Hi everyone, my name is Norhana binti Hafiz, and together with my partner Nabila Halina binti Muhammad Asri, we are students from the microelectronic engineering courses. Imagine a device that can control current without even touching it directly, just by using an electric field. That is exactly how a Jfet works, and today we'll be focusing on the N-channel junction field effect transistor. Today, we will be presenting on N-channel Jfet, a fundamental semiconductor device that plays an important role in analog electronics, especially in low noise and amplification applications. In this presentation, we will cover four main aspects. First, the device configuration, where we'll look at the physical structure and terminals of the N-channel Jfet. Second, the basic operation of the device, explaining how current flow is controlled using the gate to source voltage. Third, the characteristic of the device, including the drain and transfer characteristic that define its behavior. And finally, we will discuss the future development, limitation, and sustainable engineering considerations of the N-channel Jfet. By the end of this presentation, you will understand not only how an N-channel Jfet works, but also why it still matters in modern electronics, even with the presence of more advanced devices. Thank you, and let's begin. Unlike a BJT that use current to control currents, an N-channel Jfet use voltage to control current, and that's what makes it unique. An N-channel junction field effect transistor, or N-channel Jfet, is a voltage-controlled semiconductor device where current flows through an N-type channel between the drain and source terminals. The basic structure of an N-channel Jfet consists of an N-type substrate that forms the channel. Inside this N-substrate, two P regions are formed. These P regions are created by diffusing P-type material into opposite sides of the N-type channel. The PN junction exists between each P region and the N-type channel, and this junction plays a very important role in controlling the current flow. The two P-type regions are connected together internally. Metallic contacts are made to these P regions, and both contacts are tied together to form the third terminal known as the gate. This means the gate is actually made from two P regions acting as one single terminal. Each terminal in N-channel Jfet has a specific function. The source supplies electron into the N-type channel. The drain collects electrons from the channel after they travel through it. The gate controls the width of the channel by adjusting the depletion region formed at the PN junction. Fun fact, because the gate is reverse biased, the gate current in a Jfet is almost zero. That's why Jfet have a very high input impedance, making them excellent for amplifier applications. So in summary, the device configuration of an N-channel Jfet allows current control using voltage, making it a key component in analog electronics.
Hi, my name is Nabila Halina. I will continue to the basic operation of N-channel Jfet. VGS is a positive in order to move electron from source to the drain. At the drain, the junction is reverse biased compared to the source. The winding of depletion is by conducting to the positive voltage to the N-type material, connecting positive voltage to the P-type at the gate, so the gate is reverse biased. Source at the VGS increase negatively. The width of the depletion layer increase, the channel gap decrease. Next, when VGS is equal to 0, increases, then depletion region at drain increase and ID increase. At a particular point, the two layers will touch each other, then that point is called as pinch-off point. At a particular voltage, the two depletion will touch each other, then that point is called as pinch-off voltage. After pinch-off point, the VGS is equal to 0 or VGS is positive, then ID is become constant. Next slide. VGS negatively increase, then depletion width increases, so that channel width decreases width. For VGS constant, as VGS negatively increases, the channel width decreases.
Let's start with the ohmic region. In this region, the gate to source voltage VGS is 0. As we increase the drain to source voltage VDS, the drain current ID increases linearly. The depletion region is still small, so the channel is wide. Because of that, the Jfet behaves just like a normal resistor with almost constant resistance. Next is the saturation or constant current region. Here, the drain current reached its maximum value. Pinch-off occurs near the drain end of the channel. Even if we keep increasing VDS, the drain current stays almost constant. This maximum current is called IDSS, and the voltage where the pinch-off happens is known as the pinch-off voltage, VP. This is the region where the Jfets are usually operated as amplifiers. When VDS exceeds the maximum safe value, the Jfet enters the breakdown region. The drain current rises rapidly and can permanently damage the device, so this region must be avoided. Now, let's look at the effect of gate to source voltage VGS. When VGS becomes more negative, the depletion region gets wider. This makes the channel narrower and reduces the drain current. Pinch-off also occurs at a lower value of VDS. As a result, we get a family of drain characteristic curve for different value of VGS. Then we have the cutoff region. When VGS equals the pinch-off voltage VP, the channel is fully depleted. The drain current becomes approximately 0. At this point, the Jfet behaves just like an open switch. Finally, the transfer characteristics. This graph shows the relationship between ID and VGS while VDS is kept constant. When VGS is 0, the drain current is at its maximum value, which is IDSS. When VGS equals VP, the drain current becomes 0. The relationship between ID and VGS follows a square law equation.
I will continue to the last part, which is future development, limitation, and sustainable engineering consideration of N-channel of Jfet. Okay, next, I will go to the future development first. Although N-channel Jfet have largely been replaced by MOSFET in modern digital electronics, they continue to have relevance in specific applications. First, low-noise analog circuit. N-channel Jfet are still preferred in audio preamplifier, sensor interface, and RF front-end circuit due to their low noise performance. Second, sensor and instrumentation application. Jfet are suitable for high impedance signal detection, making them useful in medical instrument and environmental sensors. Lastly, improved fabrication technique. Advances in semiconductor manufacturing may enhance reliability, consistency, and performance of Jfet while reducing material usage. Okay, next, limitation. Despite their advantage, N-channel Jfet have several limitations. First, normally on device. The device conduct when no gate voltage is applied, which may be undesirable for certain safety critical applications. Second, limited current and power handling. Jfet are not suitable for high power or high current application. Third, lower transconductance. Compared to the MOSFET, Jfet provide lower gain and switching speed. Next, manufacturing variability. Parameters such as pinch of voltage and drain current can vary significantly between devices. And lastly, susceptibility to damage. Jfet can be sensitive to excessive voltage and electrostatic discharge, ESD. Last part, sustainable engineering consideration. From a sustainability perspective, N-channel Jfet offers several benefits. Low power consumption, the gate is reverse biased, resulting gate current and reduced energy usage. Second, long operation lifespan. Simple structure and low thermal stress contribute to durability and reliability. Third, reduce electronic waste. Longer device life help minimize replacement frequency and e-waste generation. Next, energy efficient analog design, suitable for low power systems such as portable device and monitoring equipment. Lastly, simple manufacturing process. Compared to the advanced CMOS device, Jfet fabrication can require fewer processing steps, reducing environmental impact. In conclusion, we have discussed of N-channel Jfet in terms of device configuration, basic operation, and characteristics. We saw how the gate to the source voltage control the drain current through the depletion region, allowing current control with very low power consumption. We also highlight the limitation and future development of the Jfet. Well, although it is less scalable than modern devices like MOSFET, it is still valued for its simplicity, stability, and low noise performance, especially in analog application. Overall, the N-channel Jfet remains a fundamental device that helps us understand the operation more advanced semiconductor technologies. Although simple in structure, the N-channel Jfet remains essential in building the foundation of modern microelectronic engineering. That's all from us. Thank you.